We began a discussion of set operations in the last video with intersections, an operation whose name reflects its process. The word intersection is one we're familiar with from everyday life, and its math-specific definition isn't too different. In this video, we'll focus on another operation, but one whose name also mirrors our intuition in a similar way. It's called a union. Now, when you hear the word union, perhaps you associate this with other similar words like united or unity. Unity as in the state of being joined as a whole, united like perhaps the United States, as in a collection of different states joined to form a whole country. Maybe you even think of marriage, as in the union of two people or families. The point is, all of these words represent a similar idea, bringing together two or more things to form a single larger whole. We can apply this same intuition to set theory too, taking the union of two sets to mean joining them together. We can illustrate this visually first on a Venn diagram. If we have set A and set B, we can represent their union by putting them together with this region in green. We've combined what was previously two sets to now be one single union of sets. More formally, we say that the union of sets A and B, written A union B, is the set of all elements belonging to either set, using this tailless U shape as the symbol for the union operation. In other words, the set A union B is the set of all elements X such that X belongs to either A or B. Now, in the same way I emphasized associating AND with intersections in the last video, here I'd like to emphasize the word OR with unions. We said this because an element belonged to the intersection only if it belonged to both A and B, but here an element will belong to the union if it belongs to either A or B. This will also be a useful association to keep in mind when studying logic, but for now, let's focus on set theory and apply it to an example. Consider the sets A equal to 1, 2, 3, and 4, and B equal to 2, 4, 6, 8. We saw from the last video that the intersection, the common elements between those two sets, was the set 2, 4, but finding the union of A and B will be a little different. Here, since we are combining all of the elements from either set A or set B, we can include an element if it is from either. Thus, A union B is 1, 2, 3, 4 from set A, and 2, which we've already included, 4, which we've also already included, 6 and 8 from set B. We can also look at an example where we have two disjoint sets. Say A was equal to 1, 3, 5, 7, and B was equal to 2, 4, 6, 8. And we'll take the union similarly, including all of the elements from set A, 1, 3, 5, 7, along with the elements from set B, 2, 4, 6, 8, to give us A union B equal to 1, 2, 3, 4, 5, 6, 7, 8. This may seem straightforward enough on its surface, but there is one thing to keep in mind that can get a little tricky when it comes to unions, specifically computing their cardinalities. Recall from episode 3 that the cardinality of a set is the number of distinct elements. If we look at the last example, we can note that set A had 4 elements, set B had 4 elements, and their union, the union of A and B, had 8 elements, 4 from set A and 4 from set B. Or in other words, 4 plus 4 was equal to 8 elements. This illustrates an analogy here between unions and addition. They both act similarly in the sense that they are combining two objects together, and so it makes sense that we would add to determine the cardinality of a union. However, it only works this smoothly because these two sets were disjoint, because they didn't overlap at all. On the other hand, if we consider our first example, set A had 4 elements, set B had 4 elements, but their union only had 6. The difference here is that the elements 2 and 4 belonged to both. So if we were to add the 4 from A with the 4 from B to get 8, we'd be counting that 2 and 4 twice. Since we only want to count them once, what we can do is subtract the number of elements that belong to both sets. Another way to say this is to subtract the cardinality of their intersection. The intersection of A and B is the set 2, 4, which has 2 elements. So if we take the number of elements from A, add the number of elements from B, and then subtract the number of elements that belong to both to avoid that double counting, we get 6, which matches the cardinality of the union. This allows us to make a more general formula. The cardinality of a union of two sets can be determined by the cardinality of set A plus the cardinality of set B minus the cardinality of their intersection. So for example, if set A was the set of digits and set B was the set of even digits, we can compute the cardinality of their union as n of A plus n of B minus n of A intersect B, or 10 digits plus 5 even digits minus 5 elements that both are digits and even digits. This gives us 15 minus 5 equal to 10. Now, you may notice here that this is identical to the cardinality of set A. That is because in this particular case, set B is a subset of set A. Any even digit is also a digit after all, and so the union of A and B is also still equal to A. Similarly, it is worth noting that the union of any set with an empty set is just the original set. The empty set, of course, is the set with no elements, and so taking the union doesn't add any new elements. Similar to the fact that adding 0 to any number still equals that number, taking the union of any set with the empty set still preserves the original set. Well, now we have two set operations under our belts, both of which are appropriately named to cue our intuitions, and both of which can be nicely visualized on a Venn diagram. In the next video, we'll look at another operation that fits both of those criteria as well, called a complement. And no, I don't mean like a kind statement to politely praise someone, though I certainly won't protest if you want to put one of those in the comments below related to how much you've been enjoying this video series so far. But for now, and in all seriousness, you are welcome to post any questions that you do have in the comments. Otherwise, I hope you found this video helpful. Thanks for watching, and have a great rest of your day.